Hi, good morning, good afternoon, good evening. My name is Thomas, and today I want to talk about research at the Bosch Center for Artificial Intelligence that is related to neuromorphic computing. So first of all, I want to give a short introduction to Bosch and the publicly funded project Opec. And after that, I want to discuss some selected publication. Bosch is a big company, around 400,000 people. You know the drills, the washing machines. Surprise fact number one, the washing machines is not the biggest business sector. The biggest business sector is mobility solutions. Surprise fact number two is that most likely you carry Bosch in your pockets, namely the inertial sensors in smartphones. I'm working as a researcher at the Bosch Center for Artificial Intelligence. It's mainly located in Renningen, which is near Stuttgart, but we have also sites around the globe. We are roughly 300 experts and 100 researchers. We work on various topics related to machine learning, and among others, deep learning is also a topic for us. And we attend all the major machine learning conferences. And since 2017, we are the #1 European company in AI research. Why are we doing that? Because Bosch is a company of things, and we believe that machine learning is either in the thing itself, or machine learning will be used to manufacture things. Okay, so this was maybe the boring part. Now let's come to science. So we are also participating in the publicly funded project Opec. And what is Opec about? Opec is about a smart microsystem that combines or that interconnects an event-based camera directly to a immersive device on which a spiking neural network is executed to process these events. So Bosch is contributing in terms of the industrial roadmap and also in terms of the development of algorithms for spiking neural networks. There are several academic partners collaborating and also partners from industry. And one of the first works we published in this project was a review article that I want to point you to. It's a review article about deep learning with spiking neurons. So I won't go into detail today. I will just briefly summarize it. So I think we heard it already plenty of times today. What are the opportunities? So personally, I also believe in the benefits of spiking neural networks that are sparse, asynchronous, and massively parallel. And if executed on dedicated hardware system, we get low power, low latency, event-driven systems. And what are the challenges? So the biggest challenge I see is the training of the networks, at least large-scale networks. So in this review article, we summarize different training techniques, starting with simple training techniques like conversion from analog neural networks to spiking neural networks, spiking variants of error back propagation, or local learning rules like the biological plausible spike timing dependent plasticity. And usually the high computational cost is a bottleneck for applications. So we see one solution for this if you include the learning on chip. And another bottleneck I see is the data sets. So it's really hard to find the data set where you can really show the difference between the benefits of the spiking neural networks and the benefits of the conventional deep neural networks. So back in 2018, we contributed a manuscript to Neuromorphic where we addressed the massively parallel execution of deep neural networks. And we did this on conventional deep neural networks by using so-called streaming rollouts. So if you look at the left, at the network graph, at the left of the slide, usually what people do is they use a sequential rollout. And this means they choose all connection to stay within the same time step, except of course for the recurrent connection where this is not possible. And in our opinion, this is not a very good choice. So we say the best way to roll out such a network graph is actually to choose the streaming rollout. And with streaming rollout, we mean that all connections span a time step, which is shown here in red. And this means if you want to compute the states of the neurons at a certain time step, you're only dependent on the states of the neurons from the past time step. And this allows you to compute everything massively in parallel. And we did some theoretical description of these rollouts, but we also did some empirical studies. For these studies, we used the MNIST data set. And for each sample in this data set, we added random noise to it and generated a sequence out of it, what you can see at the bottom right. And this sequence we then feed to the rollouts I've just explained. And if you do that, you can mathematically prove that the streaming rollout has an equal or shorter response time to such an input. This means the time from the presentation of the input to the output. And that streaming rollouts have the highest sampling and output frequency of all rollouts, of all possible rollouts. And to explain the short response time in our case, you can just look at the skip connection here from the second layer to the last layer. And in the streaming rollout, the skip connection is also a shortcut in time. So this means the information arrives earlier at the output and reduces the response time. And empirically, we also showed that the streaming rollouts have usually better early performance and comparable late performance. Of course, this is only a toy example, and this is why we wanted to apply this method also to some state-of-the-art machine learning example. And we did that and combined that with the conversion techniques from ANNs to SNNs to increase the efficiency. And then as a data set, we use the NCARS data set, of which you can see a sample on the upper left. So here we see all the events with on and off polarity in different colors. And what we are doing, we are generating frames out of these events and then feed these frames to a streaming rollout of the network shown here in B. And in the streaming rollout, you also see the mixture of the information as I just explained. So if you have shortcuts in time, like for example here, the blue path and longer paths, then the information mixes up and the network performs, or the rollout performs temporal integration. Here in this case, the network has 4 outputs. And for training, we just sum up the losses of all the outputs. And if you do this not only for 4 frames, but for 16 frames, you obtain the yellow curve. Sorry, it's hard to read. The yellow curve in the plot in the upper left. And this plot shows the classification accuracy, whether it's a car or not, over time. So over the output of the streaming rollout. So this means we start here at 60% accuracy and then quickly go up to 95%. What we then did is we reduced the number of frames and at the same time increase the time interval in which we accumulate the spiking events to generate the frames. And what you see here, if you collapse the full event-based signal only into a single frame, you still gain a high accuracy. And this actually means there's no temporal, or at least not a lot of temporal information, not a lot of integration of spatial temporal integration required for this task. What we did then, we converted the network from an ANN to an SNN. So we used a method by Rückauer et al. And here we encode the activations by firing rates. And then the last task was to fine-tune the step size of the simulator for the spiking neural networks. So if you choose that too high, then you will violate the approximation of this rate approximation. And if you choose the time step too low, you will generate a lot of events and you will just burn energy for nothing. And to conclude the study, we summarized everything in the lower right plot. So here you see that the spiking neural networks require approximately only 1/5 of the number of operations than the conventional neural networks. And this is especially surprising because the conventional neural networks we used were also already very energy efficient. So we did this on N cars, but also on different other data sets, like, for example, Neuromorphic MNIST, DVS gesture, and CIFAR10 DVS. And in all of these benchmarks, we achieved state-of-the-art performance with our method. Okay, so now let's come to the most recent work in our lab related to neuromorphic computing. So here it's not about spiking neural networks, so the image may be a little bit confusing. It's just a random chip. And here we focus on the parallel computation again, and especially we focus on in-memory computation. We already talked about the advantages, but the disadvantage of massively parallel and in-memory computation is that you need a lot of memory, and a lot of memory means a lot of area and usually also a lot of cost. And this is why usually the size of these chips is rather limited, and the size of neurons and synapses you can implement. So what we would like to do is we have a network, for example, for semantic segmentation. We want to fit this network onto the in-computation memory depicted here in blue. And if you try that, you see, okay, network is too big, won't fit. So something you could do with such networks is to slim them, but still too big. Yeah. You may have guessed, okay, I have to reduce the depth such that it fits. Okay, this is not enough. So I have to further reduce the depth. So now the network fits. But now the network is not deep anymore and the accuracy is really bad. So what we propose is to keep the size of the computational graph very small. And we do this by introducing a recurrent connection. And if you do that, you see it fits on the chip. Hooray, we did the job. So now let's go through that in detail. So we are working on the cityscapes data set. We especially have chosen this data set because it has a very high resolution, 2 megapixels. And our goal is to reduce the size of the computational graph as far as possible. And the network we are using is shown at the bottom. So we feed the image to the data block. The data block consists of downsampling layers and some convolutional layers for pre-processing the data. Then we have the iterative block, which also consists of multiple scales of convolutional layers. And the output of this iterative block is feedback to the input, and the weights in this block are shared over the iterations. And what you could also do, you can also feedback the signal, but also pass it to a classifier. And the classifier is simply one fully connected layer with some upsampling to go up to the original resolution. And again, we trained this network by using all the outputs. And as a loss, we use the sum of all losses of all outputs. Here, the weighted sum. And this has the advantage that we can do any time prediction. So this means at any time in the computation, so at every iteration, we can just use the newest output of the network for our task. Or to phrase it differently, if you have a fixed computational budget, you can distribute this budget over easy and difficult samples. So for easy samples, you would only use few iterations, and for very difficult samples, you may want to increase the number of iterations. And we did some ablation studies where we compared the joint training of all outputs with the training of only single outputs, which is shown at the bottom in A. And here we clearly see that early outputs in this joint training also increase the performance of the late output. If you, in addition, want to boost the performance of the very first output, so now I'm referring to the subplot C, you can just skip some of the outputs, so set the weight of the outputs to 0. And then you have less constraints and your accuracy increase a little bit. And according to the literature, we also find that choosing the weights for this individual losses to be 1 is the best choice we could find. So now we compare our networks to the state-of-the-art networks in terms of the trade-off between the accuracy, which is here called mean IRU, versus the number of MACs. And if we look at accuracy over the graph size, we see that the size of the graph is for our network much smaller than for the reference networks. Also, the latency is much lower, but at the same time, the number of MACs increases by a factor of 10. So this means in the end, it very much depends on the hardware you're using to deploy these networks to, whether, what the best trade-off is. One problem we had during the experiments for this manuscript was that if you want to unroll networks here over the iterations, it requires a lot of memory on your GPUs. So that's usually a limiting factor. So if you like to avoid this, you can also have a look at a study of my colleagues. So they presented a work called multi-scale deep equilibrium models, where you do not use backpropagation, but you use the equilibrium of a fixed point process that you optimize. So this saves a lot of memory during training. As a last slide, I want to give you a very quick overview what else happens at the Bosch Center for Artificial Intelligence. So this is again a very selected list of publications. So one very big topic for us is robustness. And many of you may already know what an adversarial example is. So an adversarial example is a perturbation of an image that can usually not be recognized by humans, but it can very efficiently fool deep learning systems. And we were one of the first to find this effect. And we were also one of the first to provide methods how you could train your network and at the same time prove that it's robust against such adversarial examples. On the top right, you see a plot from a work of a PhD student of us. It's related to neural architecture search. So he used an evolutionary algorithm with Lamarckian evolution, and he achieved results that outperformed the brute force methods introduced by Google. And at the bottom right, it's just a teaser for the work of Anna Korova and her team on the development of generative adversarial networks, to synthesize images. All right, so thank you very much for listening, and I'm very excited for open questions.